Thank you, Chair, for the presentation. Good afternoon to everyone. This topic is, which is still in progress, is developed in collaboration with colleagues from University of Calabria, in this case with Professor Lonetti. Okay. How can I? Sorry. Okay. So this is a brief overview of the presentation, an introduction, research goals, materials and methods, results and discussion, conclusion, and acknowledgement. In general, we use composite material in the construction field for repairing, as is here reported in this photo on the left, or as construction material. In this case, we are speaking about pultruded profile. The name came from the industrial process to produce this material is pultrusion. In this case, we have a unidirectional fibers embedded in a thermoset matrix. Within this material, in general, using thanks to the high anti-corrosive properties, these material are in general, okay, in this case the video doesn't work, but this kind of material are used especially in aggressive environments. In this video, my idea was to show you this kind of material in contact completely all their life with water. In this case, tap water. We are speaking about a cooling tower, or are used for, like in this case in Germany, to replace a previous concrete bridge with a new one in glass fiber reinforced polymer. Okay, now the video is going. All these kind of structures involving GFRP materials member are connected each other by bolted connection, adhesive connection, or a combination of these two technology. In general, we can see that the adhesive connection is the best one for this kind of material. We know from literature what about durability of fiber reinforced composite material, and we know that for a period of 9 months was experimentally demonstrated that the mechanical properties can decrease of about 10% to a maximum of 50%. But what about the adhesive that we use to repair or to build a pultruded profile? For example, in this case, we have a technical resin. One is on the left is a Cicadur 30. On the right, we have Araldite from 2 different companies. And what is reported probably here is is that the thermal properties like glass transition temperature is a function of curing the temperature. And also, obviously, the strength of the mechanical properties of the resin is a function of the time and the temperature. High curing temperature is not always possible to reach because in civil engineering we are speaking, we can have a logistic problem. For example, for Cicadur 30, the best temperature to obtain the highest glass transition temperature is 45 degrees, which is not very easy to reach in our field. So the consequence is that TG is not always the highest possible. In civil engineering application, ambient temperature is the most common situation we have. So the goal of the research is try to increase the thermal and mechanical properties of adhesives cured at ambient temperature by adding nano additives into the binder in order to increase the glass transition temperature, or into the hardener in order to increase the strength of this material, with particular regard to the hygrothermal durability. The first step in order to achieve this goal was to study two commercial epoxy resin as they are. The first one was Cicador 30 and the second one was Araldite. We cured these both resins at room temperature, 23 degree in this case. Their technical data sheet report these two glass transition temperature. We study, first of all, we study the thermal properties of two resin. Here we have results for Cicadur, and here we have results for Araldite. If we point our attention on these two graphs, is evident that the glass transition temperature for the Cicadur 30 was evaluated like 45, lower than the maximum glass transition temperature obtained, but a more elevated temperature. So that one of Araldite is 70, is quite similar to the highest possible. The curing degree of this resin, according to this room temperature curing, is 82% for Cicadur 30 and 97% for Araldite. We have performed a huge experimental program in order to evaluate the behavior of adhesive in contact with seawater and tap water. In particular, we built adhesive, quite 200 adhesive joints. Adherence was in GFRP, and the adhesive was Cicadur 30 and Araldite. We selected the temperature of 30 degrees to liquid, seawater, and tap water. The observation period was 15 months. And we evaluated the fracture energy in mode 2 by end-notch failure laboratory test. This is the absorption results relative only to the adhesive. Here we have seawater, Araldite versus Cicadur 30. Here we have resin in tap water, again Araldite versus seawater, and here we have the absorption behavior of joints, of adhesive joints. In this case, we have adhesive plus adherence in glass fiber reinforced polymer. In order to evaluate the fracture energy in mode 2, we use a end-notch failure test. The geometry of the specimen is here reported. We use, in order to evaluate the fracture energy, and so also the air curve, or cold resistance curve, the compliance beam basic method, which is the convenience of this method is that the fracture energy is a function of the initial compliance of the specimen and the equivalent, the initial crack length, instead of an equivalent crack length. We evaluated for both adhesive 3 points. We know the most common one are Pmax and PU. At Pmax, the cracks starts to grow. At PU, the cracks stop. From this point to this point, we evaluated the resistance curve. We evaluated also in these curves this point, which is detect the end of the linear elastic behavior. On the air curve, we can see that this refers to the Cicadur 30, which is a linear elastic behavior. In fact, this resin has a brittle failure. This air curve refers to the Araldite, which show a more ductile behavior than the other adhesive testing. Parallel to this three-point load, we can evaluate the 3 different fracture energy. This one is the classical fracture energy, and this one, the first point, is the fracture energy at the end of the linear elastic behavior. We evaluated finally the fracture energy for unaged specimen, for aged specimen in seawater and in tap water. As is possible to see, we don't have a great decrease in terms of strength and stiffness for specimen with the Thicadur 30, but we have a sensible decrease in terms of strength and terms of stiffness when we use Araldite adhesives. If we make a graph of fracture energy, fracture energy over the time, we can see that we have a reduction in terms of fracture energy of 20% for Thicadur 30 and 60% for Araldite. Okay, we have evaluated in order to transform the fracture energy in interface law for design purposes. We have developed a numerical analysis evaluating parameters which influence the behavior of these joints. We have a perfect agreement between numerical and experimental results. We have translate fracture energy in interface law, finding the shear strength in the case of tap water, in the case of seawater. Now we have completed the study of state of art of these two common commercial cold curing epoxy, and now we are ready to try to modify the glass transition temperature. We have also to take into account that our standards limit the use of service temperature of about 15 degrees lower than the glass transition one. So our idea is to increase the glass transition temperature and also curing degree by using a nano additive. Thank you for your attention.